Right. Sorry I'm late. No? I encountered unexpected traffic. Are you okay? I'm curious. How many okay. How many of you are attending a class in UP for the first time today? Oh my. So hindi pa nyo alam talaga yung buhay dito sa campus. No? So this is going to be an experience for you. Okay, so we're having our first Triple E 131 face-to-face session. We're also on Zoom. I cannot see the Zoom participants, but I'm assuming they're there. They can hear me. Okay. So just some things that I want to emphasize for this particular session and for the sessions to come. No? First of all, let's not be too formal with each other. Okay. And then help me make the class as interactive as possible. How are we going to do that? Okay. When I ask a question, say out what you think the answer is. Don't be scared, you might be wrong. I mean, of course, pag-isipan muna niyo yung tinatanong ko, no? But the reason why I ask questions during the class is to stimulate your thought. So say out what you think the answer should be. Okay. When I ask you to solve for something, please try to do so. Subukan yung gawin. Huwag lang kayong aasa dun sa mga katabi nyo, no? Or wag na lang, titignan na lang yung ginagawa ng mga katabi nyo. Okay, and if you want to interrupt me anytime, you may, if you have a question. Interrupt me anytime if you want to. Just shout out, no? Sir, or whatever, no? Whatever you want to say. Kahit na, hoy! No? Okay, and for me, there's no such thing as a stupid question. I don't consider any question to be so stupid. In fact, a lot of times, students hesitate to ask questions in class kasi baka sabihin daw ng mga ibang kaklase nila, hindi niya naiintindihan to, napaka-tanga naman yan, no? But actually, when you ask questions, you're probably helping so many other people. You're probably helping more classmates than you know you are. No? So, like I said, there's no such thing as a stupid question, okay? Okay, so let's make this worth the effort both you and I are making in coming here. So you know that face-to-face classes are not yet a regular occurrence here in UP Diliman. This is some sort of a pilot. I volunteered to be part of this pilot, and the reason I did that is, and this is proven by international studies, the most effective mode of instruction is still face-to-face. That has been proven time and time again, no? Despite all of the data that has been collected during this pandemic. And it's more effective than any other mode of instruction, not only for the students' learning, but also for the students' mental health. Okay. So let's make this worth the effort both you and I are making in coming here. So what are we going to do today? We're going to start with Module 4. This is the first session in Module 4. Unfortunately, I think the material for Module 4 has not yet been uploaded in Google. Apologies for that. We hope to upload all of this material by tomorrow. But just as I always do, this session is going to be made available to you through Uvle. I'm going to post this session through Uvle. There's supposed to be a recording of this session too over Zoom. I don't know whether that's being done. Yes, no, it's already being recorded, and we will make that available also to you so that you can review the session later on. Okay, so MOS transistor amplifiers. So we have 3 configurations. You have 3 MOS transistor amplifier configurations. You have your common source, your common gate, and your common drain. Okay? And the configuration is based on what terminal is considered to be common. Pag sinabi natin common, this is common with respect to the time-varying input signal, with respect to the AC input. When we say with respect to the AC input. So yung common source natin, your input is your gate, and your output is your drain. So the source is common. The source is common. So we show 2 configurations here. This is for your NMOS, and this is for your PMOS. Yung common gate natin, yung common. The gate is common. So the input is at the source and the output is at the drain. That is your common gate. Again, I show this for both the NMOS and the PMOS. And finally, the common drain, your input is at the gate and your output is at the source. Okay. Pag tinignan niyo yung common drain, for example, taking a look at this, no? The NMOS common drain, tatanong niyo, no? Paano naging common yung drain? Hindi ba nandito sa taas yung drain? Yung ground ko nandito and ground connotes common. So how did the drain become common in that particular case? Well, like I said, the common terminal is with respect to the time-varying input or the AC input. Now you're going to learn later on that when you're doing AC analysis, your DC sources are suppressed. It's part of superposition. You learn superposition. Remember when we're doing AC analysis, we split up the input signal into its time-varying component and its bias, no? And its DC component or the bias. We do that. And when we do the analysis, we separate the analysis of the bias or the DC component and the time-varying component. When you consider only the time-varying component, your DC components are equivalent to short circuits for voltage sources and open circuits for current sources. So with respect to AC, your VDD is actually suppressed or connected to ground. And that's why this became the common with respect to AC. Yeah, this is common drain. That's going to become much clearer later on. Okay, so we'll first discuss the common source amplifier. How are we going to develop or how are we going to show the characteristics of your common source amplifier? We're going to do this through the voltage transfer characteristics or VTC. The voltage transfer characteristics, when you say transfer characteristics, pag sinabi nating transfer characteristics, that is usually output versus input. So this is output versus input. Okay? So when we say voltage transfer characteristics, then we specify output voltage versus input voltage. And you were already introduced to that in previous sessions. In fact, in EEE 123, that was already introduced to you when you took up the op-amp. You studied the voltage transfer characteristics of the op-amp. So we are going to characterize your common source amplifier by studying its voltage transfer characteristics. Now, how will we get the VTC or the voltage transfer characteristics of your amplifier? Well, we're going to do this the brute force method kasi yun lang alam natin ngayon. No? Ang gagawin natin, may pagka-brute force. Gagawin natin to point by point. Ipa-plot natin point by point. And to plot the transfer characteristics point by point, ang gagamitin natin yung large signal model ng MOS transistor. Napag-aralan na natin yan. These are the large signal models of your MOS transistor. This for NMOS and this for PMOS. And in your large signal model, you have two equations, one for saturation and the other for linear operation. For NMOS, this is for linear and this is for saturation. For PMOS, it's the same equation. Nagbabaliktad lang yung subscripts natin. And instead of dealing with VTH, we deal with the absolute value of VTH. Bakit? Ano yung sign ng VTH pag PMOS? It's negative. So when we reverse the subscript, we deal with the absolute value of VTH. Okay, so using these equations, I can, for example, get a set of input values and determine the set of output values. And where do you remember having done that? Nagawa na niyo yan. Where do you remember having done that? That I made you do that in the problem set. Naalala niyo, you did that in the problem set for was that module 2? Yeah, module 2. So let's pursue that problem in the problem set. No? So ginawa natin to sa problem set. We did it for a PMOS amplifier. I modified the parameters slightly. Okay. I think I changed the value of K and I changed the value of R sub D. So gawin natin yan. Okay. We just refer to a few notes. Okay. When V sub I is small, sa tingin ninyo, what is more likely? Will it be linear or will it be saturated? Pag maliit yung V sub I. Just think about it a little. Small V sub I, will it be linear or will it be saturated? Anyone? Okay, kahit na humula naman kayo, no? Okay, let's think of it this way. No? Pag V sub I is small, ano ang value ng VSG? Will it be large or will it be small? Okay. Ingat kayo sa sagot. Okay. Here's VSG. So when V sub I is small, what is the value of VSG? Large. No? When you have a large VSG, of course, you are not cut off. Obviously, pag malaki yung VSG, you're going to be either in linear mode or in saturation. Okay. Current will flow, definitely. Okay. If current flows, you're going to have a voltage across R sub D. If you have a voltage across R sub D, then most likely the voltage across your source to drain will be smaller than VDD. In fact, not most likely, obviously. No? Kasi kung may voltage ka across R sub D, then the voltage from here to here should be smaller than VDD because this plus this should equal VDD. So you have a large value of VSG, you have a smaller value of VSD. What is the mode? What is the most likely mode? Okay, that maybe is making you think a little bit. Pag malaki yung source to gate, pag PMOS, or gate to source, pag malaki yung gate to source, mas maliit yung drain to source, or source to drain, depending on PMOS or NMOS. Okay. The tendency is for you to be in linear mode. So for small V sub I, the tendency is to be in linear mode. Okay. You remember our graph of the output characteristics for MOS? Let's say this is PMOS ang pinag-uusapan natin, no? So pag PMOS, this is a graph of ID versus VSD. Okay, and for a particular value of VSG, that will look like this. Okay, for a particular value of VSG. At some point here, you have what is called VSD SAT, capital VSD SAT. Okay, to the left of that, this is linear, and to the right of that, that is saturated. Diba? Kasi pag saturated, yung I sub D natin is independent. Well, at this point now, we'll say I sub D is practically independent of VSD. It is only in linear mode where I sub D varies with VSD. So you just remember that there's this threshold, VSD sat. Okay. When VSD is greater than that, you are saturated. When VSD is less than that, you are in linear. Now, what's the value of VSD sat? VSD sat is equal to VSG minus the absolute value of VTH. Right? So when you have a larger VSG, when VSD is greater than this value, okay, when VSD is greater than this value, you are insaturated. When VSD is less than this value, you are in linear mode. Okay? So pag maliit yung V sub I, malaki yung VSG. Maliit yung VSD. No? Malaki yung VSG, maliit yung VSD. So you're most likely to the left of this line. So you will be in linear mode. And so we can compute for the value of V sub O. Okay. So at V sub I equal to 0, okay, you're going to use the equation. Okay, first of all, at V sub I equal to 0, you have VSG. This is equal to VDD minus V sub I. Okay. This is going to be equal to 10 volts. And then you use the equation I sub D is equal to K VSG minus absolute value of VTH minus 0.5 VSD multiplied by VSD. Okay. So that's because we had a hint it was in linear mode. Otherwise, you can assume. Ginagawa nyo yun. No? In fact, usually, ang unang assumption ninyo is it is in saturation, and then you have to validate your assumption. But before you assume, you can already make an educated guess based on what I just said. Anyway, your educated guess is this. Pag malaki yung value ng VSG, okay, there's a pretty good chance VSD is going to be smaller, and therefore you're in linear mode. Now then, pag maliit yung value ng VSG, there's a good chance your VSD is going to be bigger, and therefore you will be in saturation. So anyway, when you do the computations, no, of course, this is only one equation. You're going to have another equation. Your other equation is I sub D is equal to 10 minus VSD over RD. Okay. VDD, no? Sorry, not 10, VDD, no? Sinabi ko na 10 dito. Anyway, sige, let's leave it at that. So this is your second equation. And then you solve this simultaneously. Take note, there will be two roots. And ito laging nagkakamali yung mga estudyante dito, no, during the exam. Kasi masyado kayo na-spoil ng calculator nyo. Ginagamit na lang nyo basta-basta yung solve function. So ano lumabas doon, yun na sinasagot niyo, no? You forget to validate. And I noticed some people, even in the problem set, did that. No? So you're going to have two roots. You should choose which of those roots will be valid. And the way you do that is you choose that the root that you are selecting really satisfies the condition of linear operation or ohmic operation. Okay. And if you do this, you're going to get okay, let me just give you the answer. No, you're going to get two roots. Okay, one is going to be 18.36 volts, and the other is going to be 0.44 volts. No? Obvious, hindi pwede to. This is very unlikely. Itong 18.36 volts. Okay, first of all, our VDD is 10 volts. Paano magkakaroon ng 18 volts dito? The only way this will be 18 volts if VSD is negative. That is the only way this will be 18 volts. If VSD is negative, we already know that it's not going to be operating in linear mode. Kasi baliktad yung voltage across your source and drain. So obviously you count this out. Okay, this is going to be your voltage, and then you're going to get V sub O is equal to 9.56 volts. No? So that's one value that you can already plug in here. This is going to be 9.56 volts, and the operating mode is indeed linear mode. Okay, and so you do that for, well, I was going to go through that here, no? But maybe you don't need that exercise anymore. Practicing na lang yun sa bahay. Okay, I went ahead and did it for many values. So again, this is using the brute force method. Several V-ins I computed for several V-outs. Okay, I had the help of Excel. Of course, you can also do this through simulation, but I wanted to come up with a specific values point by point. Okay, and this is what I get. These are my voltage transfer characteristics. So you see, here you're operating in linear mode. Okay, you're in linear mode until Vin is about 6.4. Actually, I put in more points between 6 and 8 volts because I saw that that's where it started dropping. That's why siningit ako ng points doon, no? So you see that you're in linear mode until about 6.4 volts. So that is somewhere here, no? This is linear. Okay. So this is the transition. Okay. This is the sorry, no, hindi pala dyan. Ito, no, dito. This is the transition from linear mode to saturation mode. And then we're in saturation mode until about 9 volts. Okay, so until about 8 volts, no? So this is saturated. Okay, and then here, this is the transition to cutoff. Okay, and it's understandable why the transition will be at 9 volts. At 9 volts, your V in is going to be, sorry, at V in equal to 9 volts, your VSG, your source to gate voltage is going to be 1 volt, and 1 volt is your, no? 1 volt is your threshold voltage, right? Or -1 is your threshold voltage. Remember, you're only going to get conduction when VSG is greater than the absolute value of your threshold voltage. Doon lang magko-conduct tong transistor na to. That's why you expect that pag VSG is equal to 1 volt, dito, that is V in equal to 9 volts, VSG equal to 1 volt, that is your transition. And then here now you're going to be cut off. From here to here, cut off ka na. Okay. So that's the voltage transfer characteristic curve. Now we said this is going to help us determine what the characteristics of this amplifier is going to be. Okay. So first of all, no, I don't want to look at the gain yet, no. Let me add a slide. Okay, so sabi natin ito yung VTC. Use a different color. Sabi natin ito yung VTC. It looks something like this. Okay. So we already discussed this before when we were discussing the BJT as an amplifier. What if my input is this way? Okay. What if this is my V sub I? This is my D small I. Okay. What do I expect my output to look like? If this is my input, okay, if I project that upward, my change in output is going to be here. Dito maglalaro yung output ko. Right? As my input changes, my operating point is just going to be playing here. So if I plot that versus t, if I plot my output versus t, v sub o, that's just going to be a straight line. Why? My transistor is cut off all the time. What do I have to do so that I will see changes in my output as my input changes? Anong kailangan kong gawin? I heard it. What do you have to do? You have to bias the input. How do you bias the input? You have to offset it. Now, how do we offset that? We have to offset it to the right. Kailangan ito, gagalawin ko toward here, so that as this changes, yung operating point mo, akit pa baron. So that's the purpose of, sorry about that. So that's the purpose of biasing. Right? So ang gusto ko mangyari, ito, ita-translate ko dyan. So that it will now appear here. And this is now my bias. This is my bias voltage. Okay. So ngayon, habang gumagalaw to, asan yung operating point ko? It will be up and down here. Okay. So if I take a look now at my output is going to be, well, actually, as this goes higher, this is going to go lower. So habang tumataas yung input ko, bumababa yung output ko. Right? So it's going to be this way. Okay? Your gain is negative. Okay? And it's important to choose a bias voltage properly. Importante yun. Because if you bias it improperly, for example, no? What if okay, let me okay. What if again this is my transfer curve. See, that's my transfer curve. What if I biased it here? Ano kung ito yung bias ko? This is my bias. And so my input changes this way. Okay. What will my output look like? Pag tinignan ko yung output ko, okay, if I take a look at my output, so I'm going to be playing here, no? But at some point, andun na siya sa kaliwa, no? Nandun na siya sa kaliwa. Okay, as my input increases, okay, bababa siya na maganda. But as my input decreases, at some point, matataba siya rito. It's going to get cut. And so you now see that because your bias point was not good, you don't have the maximum possible output swing. That's why it's important that you bias your transistor properly. So the same concept that you studied in the BJT, importante yung biasing. So that is what you mean by bias. Okay, now let's talk about gain. Let's talk about gain. What is gain? Gain, okay, this is actually the change in voltage, the change in input, a change in output versus change in input. No? This is change in output over change in input. So for this particular amplifier, okay, this is dVo over dVi. We're still talking about large signal. No? We're still talking about large signal here. Di pa tayo nag-do small signal analysis. Okay. We can actually compute for the gain when the transistor is saturated. Okay, bakit? No? What is ID? ID is equal to 1/2 K. Okay, this is a PMOS, so this is VSG minus the absolute value of VTH squared. That's ID. Okay, and VO. What is VO? VO is VDD minus ID times RD. VO is VDD. No, sorry. I'm thinking about VO is just ID RD. Sorry. I was thinking about the NMOS. This is just ID times RD. Okay. Ulit mo. Tignan nyo rito. VO is just ID multiplied by RD. Okay. Now, VSG in this particular case is VDD minus VI. VSG is VDD minus VI. Okay. So VO, okay, is equal to RD. So ilabas natin itong RD na to, multiplied by 1/2 K VDD minus VI, okay, minus VTH squared. You follow? Susundan nyo? So I can now get dVo with respect to dVi. Just get the derivative of this expression with respect to VI, right? And what will that be? These are all constants. So 1/2 RD at saka K. 1/2 RD K. Those are all constants. So you get the derivative of this quantity. That will be 2, okay, VDD minus VI minus VTH, okay, times the derivative of the inside. What's the derivative of the inside? Practice the derivative. Anong derivative nitong term na to, yung sa loob? Derivative nito is 0. That's a constant. Derivative nito is also 0. Anong derivative nito? -1, right? So this is times -1. Okay, this 2 cancels out. Okay, so I'm going to end up with negative RD K VDD minus VI minus VTH. That's my gain. This is pag saturated. So you can actually compute for your gain for this particular amplifier when it is saturated. Okay? And notice that the gain is a function of your input voltage. Your gain is not independent of your input voltage. Now it's difficult to do the same thing when you are in linear mode, because when you're in linear mode, then your current ID is dependent on two things. It's dependent on both VI and dependent also on VSD. So mahirap makakuha ng closed expression for V sub O in terms of V sub I pagka ganun. So you're not going to be able to do that in linear mode. Anyway, what I did for linear mode, I just used approximation. Kasi pwede ko namang i-approximate yung gain, no? Delta V sub O over delta V sub I. From my previous table here, dito sa linear mode, I can just get the change in V out versus the change in Vn, and that's my gain. But here in saturation, I can actually compute for the exact gain using the formula that I just derived, using this formula. And I just plotted that. And this shows you what the gain of your amplifier is going to look like, of this particular amplifier. It shows you what that's going to look like, okay, for particular value of input. Okay, when you choose your operating point, okay, I already showed you earlier, one of your criteria in choosing the operating point is your output swing. You want a good output swing. You don't want your input to be clipped. No? Kanina pinakita ko yung clipping. So another criteria for choosing your operating point is your gain. You might want a specific value of your gain. For example, do you want to maximize your gain? Because if you wanted to maximize your gain, then I would be operating my amplifier maybe somewhere in this area. First of all, we already said you should operate your amplifier in saturation, because that is where it operates most linearly, no? When it is in saturation. No? Sinabi natin dito. We want to operate our amplifier here, somewhere here, no? When it is saturated. No? We don't want to operate it here, no? Because of its nonlinear characteristics there. Okay? So I want to operate my amplifier somewhere here. So now you see a trade-off. If I operate it, for example, if I operate it at this point, yun yung operating point ko, medyo mataas yung gain ko, pero limited yung output swing ko. Right? Because if I operate it at this point, okay, medyo tumaas lang yung, is it tumaas? Sandali, no? Bababa. Yeah. Okay, if I operate this at this point, okay, then I tend to hit linear right away. Okay, I will hit linear right away. No? But then I have higher gain. If I operate it at this point, I will not hit linear mode right away. No, but then I have lower gain. So it's a trade-off. So those are the trade-offs that you make in choosing your bias point. One is, okay, your output swing, and then the other is your desired gain. Okay, this example that I just gave, it's not the usual example given in books as an introduction to this subject matter, because PMOS, no, usually NMOS ang unang pinag-uusapan, no? So I just, for completeness purpose, I just showed you, okay, what if this had been an NMOS? So this is more traditional, no? Pag NMOS. So this is what an NMOS common source amplifier will look like, if you try to get what the equivalent of this is for the BJT, it would be your common emitter amplifier pagka BJT. So here we're now talking about VGS. No? So these are the subscript that you're more used to. VGS, V sub O is equal to VDS. Okay, this is ID. Okay, and this time V sub O is VDD minus ID times RD. Right, and V sub I is VGS. Okay, same parameters. I went ahead and did my brute force point by point computation. And you're going to see some subtle differences. Okay. Dun sa PMOS, kapag maliit yung input ko, ano yung output ko? Is it linear or is it saturated? It's linear, di ba? Pag maliit yung input ko dun sa PMOS, I start out with it being in linear mode. Tapos habang lumalaki yung input ko, it transitions to saturation. And then when it is very large, it becomes cut off. Dito ngayon sa NMOS, kapag maliit yung input ko, I start out by it being cut off, which makes sense. Kasi pag maliit yung input ko, ibig sabihin yung VGS ko, my gate to source voltage is small, it is not exceeding the threshold voltage, so it will be cut off. Habang lumalaki ngayon yung input ko, it transitions to saturation. So habang lumalaki, nagiging saturated. And then pag malaki na, it transitions to linear. So you see that there's a difference in the progression. Pag PMOS, it starts linear, okay? And then saturated, then cut off. Here it starts cut off, then saturated, then linear. Okay? And you should be able to determine, anyway, you can do this as an exercise. You should be able to determine the transition from saturation to linear. In this particular case, that's why I outlined it as a parang irregular yung mga values, no? 3, 3.2, 3.4. The reason why I put 3.46 here is because I computed that to be the transition between saturation and linear. Okay, but take a look at the curve. The curve looks the same. Okay? The curve looks the same as the PMOS. In other words, the two will amplify in the same way. Okay? It will amplify in the same way. Except that, where do I need a bigger bias voltage? Dun sa PMOS or dun sa NMOS? Dun sa PMOS, di ba? Dun sa PMOS. Kasi yung PMOS curve ko parang ganito, pero medyo dito siya bumaba. No? Kanina dun sa PMOS. Therefore, I need a bigger bias voltage. Here, I need a smaller bias voltage. So what you can do with the PMOS, you can also do with the NMOS. Basically, that's my message. Okay, so this is what the book will show you. So I picked this up from Cedra and Smith, these charts. In fact, I even point out the page. Okay. So this is the typical voltage transfer characteristic curve of your transistor. You start at cutoff. Okay, when your input, remember VGS is your input. When your input is equal to your threshold voltage, that is your transition from cutoff to saturation. Okay? That's the transition from cutoff to saturation. Dito sa point A. At some point, you're going to have an input voltage, which is your transition from saturation to linear. The triode mode is another term for linear mode. No? Actually, there are three terms that you can use: the linear mode, triode mode, or ohmic region. No? Those are the three interchangeable terms for linear. So this is the transition. Okay. So this is VDS at point B, which is VGS minus V sub t. No? Remember what we call that VDS sat? This is actually VDS sat, okay, which is equal to VGS minus VTH. We're talking about NMOS now, kaya wala na yung absolute value. It's just, okay. So ito, no? Okay, that is what the output is going to be in the transition, because that is at that point where exactly, right, VDS is equal to VGS minus VTH. Again, if you remember the curve that I drew earlier, the curve natin ganyan. Again, you remember this is VDS sat, okay, and this is VGS minus V sub VTH, no? Where VGS is the gate to source voltage applicable to this particular curve. We're talking here about VDS versus ID. So yun. Ito yung point na yun. No? Okay. And what is point C? Point C is when you're deep in linear mode. Deep in linear mode, where your output is already very small. Your drain to source voltage is very small. So if you take a look at that with respect to the characteristic curves of your NMOS amplifier, so these are your NMOS amplifier characteristic curves. This is your load line. Okay, what is your load line? The load line is the equation of your relating I sub d, R sub d, and your output. No? So your load line in this particular case is VDD minus ID RD is equal to VDS. VDD minus ID RD is equal to VDS. So that's the equation of this line. Okay. The slope of this is -1 over RD. No? Okay. Okay, so this is cut off. Ito yung point na cut off tayo. In other words, this corresponds to your VGS is less than VTH. By the way, dito sa libro, it calls it VT, no? Hindi VTH. So it's just a difference in term. Pag nakita nyo sa Severin Smith na VT, that's VTH. No? So these are now when your VGS changes. So this is for a larger value of VGS, a larger value of VGS, a larger value of VGS. No? So this is increasing VGS. So imagine natin dito, lumalaki itong value na to. Okay. You get to a point where you're operating now here, no? And that is the transition from saturation to linear. So that's point B. That is your transition from saturation to linear. So yung VGS na ina-apply dito, okay, is actually your input that will cause the transition. Itong VGS, well, it calls it here VGSB, no? That's this, no? VGS at point B. Yan yung VGS na ina-apply dito. Okay? And if you increase VGS further, you're pushing the operating point up here to C. So this is when VGS is already VDD. You're pushing the operating point up here to C, where you're deep in the linear region. Okay, so andito na tayo ngayon. So that's what your transfer characteristic curve will look like. Okay. Any questions so far? Masyadong tahimik, ano? It's scary when the class is very quiet because it only means one of two things. Either naintindihan nyo o wala kayong naintindihan. So that's a little bit scary. Okay, so I just wanted to show you the different points of operation based on the characteristic curve. So again, we will choose our bias point somewhere between A and B. That's where we will choose our bias or our operating point. So what do we want? Do we want maximum gain or maximum swing? If we wanted maximum swing, we'll put it probably somewhere here in the middle. No? If you wanted maximum swing, you'll put it somewhere here in the middle, except that you're going to get distortion right away. Kasi konting baba lang ng input voltage natin, we already hit cutoff. Okay. If we want maximum gain, I'm going to put my operating point somewhere here. Right? But again, there's going to be some trade-off, no? Because I increase my input. After some small increase, I'm going to hit already linear mode. So those are the trade-offs. Any questions? Okay, your expression for gain for the NMOS common source amplifier. So again, no, my output V sub O is equal to VDD minus ID times RD. Okay, this is VDD minus what is ID? ID is 1/2 K. This time this is V sub I. VGS is V sub I. Itong VGS, that's my V sub I. This is my V sub O. VDS is my V sub O. Okay, V sub I minus VTH squared multiplied by RD. So this is in saturation. What is my gain? Your gain is DVO, dVi. Derivative of this is 0. You're going to have minus 1/2 K 2 VI minus VTH. The derivative of this inside term is 1. Okay, and then you multiply that by your constant R. So this cancels out. Okay. So it's going to be minus K RD VI minus H. That's your gain. Negative means 180 degrees out of phase. Alam na nyo yun, no? As your input is increasing, your output is decreasing and vice versa. What affects your gain? Okay. What affects your gain? R sub D, the value of the resistance, K. Later on, you'll learn a little bit more about K. This is what we call your transconductance. Okay. And also VTH. VTH also affects your gain. So if you want a large gain, no, during the semiconductor manufacturing process, you can process a transistor with a large value of K. Okay, and the value of K will depend on the dimensions of your transistor. Later on, you're going to study that. You're going to find out that as you increase the width of your transistor, the value of K becomes larger. So you can increase K, or kung nandiyan na yung transistor niyo, you can also increase R sub D. increase R sub D, you increase the gain of your amplifier. That's what's pointed out by this equation. Again, it's hard for me to come up with the same expression for your transistor in linear mode, when in the first place, you don't use your transistor as an amplifier in the linear mode. No? You always bias it so that nandun tayo sa saturation mode, not in linear mode. But I plotted the gain anyway, using approximation, and this is what my gain will look like. So I'd like to operate my amplifier somewhere here while it is in saturation. Okay. I wonder if I can show you some demo. No? I'll just try. No? I don't know if I have a good internet connection here. Okay, lumabas, no? So I can actually show you the voltage transfer characteristic curves. So this is, for example, for an NMOS. Okay. So this is an NMOS amplifier. What I did was I just created an input voltage that just sweeps. No, it's just a ramp to sweep the input from 0 to. I'm just sweeping the input from 0 to 10 volts. Yun ang ginagawa ko rito. It's a ramp that sweeps the input from 0 to 10 volts. The period is its frequency is 2 kilohertz, so 500 microsecond period. Okay, and then what I want to show you is, okay, I want to show you the input on the. Okay. No, let's see. Yeah, no. The output is going to be on my vertical. Let's see what it looks like. Sorry. Yeah. Yeah. The output is going to be in my vertical axis. So this is my output. And my input is in the horizontal axis. Then in green is my output. My input is in the horizontal axis. So this is just plotting the output versus the input. Okay. Now I'm going to show you that if I adjust the value of K here, okay, lakihan ko yung value ng K, what's going to happen to my curve? It gets steeper. Yung curve ko, let's wait for it to clean up. It got steeper. Mean to say, for a smaller change in input, mas malaki yung change ko sa output. My absolute value of my gain actually increased. Okay, so let me bring this back to the original 5 volts. Okay, so now I get a smaller gain. Okay, I can actually adjust the value of K. Okay, this is the value of my K. I can increase that. And notice what happens. Again, my gain increases. So that just shows you that K affects the gain. Okay. And what else can I show you? Okay. This is the same amplifier. My input now is a sinusoidal quantity. Okay. Let's say I don't have any offset voltage. So yung voltage na nakikita nyo dyan, yung V, that's actually an offset voltage. Think of it as your bias. So itong V na to, think of that as your bias. So if I don't have any bias, what's going to happen? You don't expect it to have any output. So if I play the simulation, okay, you see my input is changing. The input is the purple curve, and my output is flat. My transistor remains cut off because my input doesn't even reach the threshold voltage. Hindi umaabot yung input ko sa threshold voltage. Now what I can do is I can bias this by adjusting that DC voltage. I can add a DC voltage. Okay, so let's say I bias it by 100 millivolts pa lang yan. That's 1 volt. So I lifted it by 1 volt. Kita nyo, may lumalabas na output. Ano? Okay. And if I increase the bias, okay, so you see now that there's an output and there's amplification. You can see that the output is larger than the input. You can also see that it's 180 degrees out of phase. Habang lumalaki yung input, lumiliit yung output and vice versa. Okay? But if I over bias it, what happens? Okay. First of all, nagki-clip na siya, no? Okay, it's now heavily distorted. Okay, that's what happens when you over bias it. So you have to find that good balance. Now the other thing that I wanted to point out is the other thing I wanted to point out is the gain is not that big. If you take a look at the values of gain here, okay, ito yung mga values ng gain. In fact, medyo maliit, ano? The gains are small. Well, dito mas mataas yung gain, no? Sorry, this is the BTC. Yeah. Here you have larger values of gain. There's something wrong here. Well, yeah. I better check those figures, no? But like here you have higher values of gain. Dito sa PMOS. I'll check the figures for NMOS, baka may mali ako sa computation because it shouldn't be that small. But the gain is not that big. You recall the gain in your BJT? Ano yung mga values na nakuha mo din? You recall? Ano yan? Yeah, umabot ng 100, di ba? 100 or even bigger than 100. Dito sa MOS, it's probably going to be single digit. Mataas na yung double digit. At ganun lang yung gain sa MOS. So if you want large gain amplifier, usually BJT is still your go-to solution if you want a large gain amplifier. But of course there are other advantages to using MOS. Later on you're going to study what those advantages are. Okay, so what else? Okay, so there are other amplifier configurations. For example, you have your NMOS common gate amplifier. So this is NMOS ngayon to, common gate. Your input is at your drain, okay, and your output. Your input is at your source, and your output is at your drain. And the common terminal with respect to your time varying input is at your gate. Okay, so these are the equations that will govern now your inputs and outputs. So if you take a look, this is now VGS. Okay, that is VGS. what is VGS equal to? Take a look, VGS is equal to negative V sub I. If I do a ADL here, I'm going to have V sub I plus VGS is equal to 0. Or V sub S is V sub I is equal to negative VGS, or VGS is negative V sub I. Now VDS is V sub O minus V sub I. Right? This is my VDS. It's V sub O minus the voltage at this node minus the voltage at this node, V sub O minus V sub I. And V sub O is VDT minus IDRD. Okay, so those are the equations that you will combine with your large signal model equations to be able to come up with this. I can do that as an exercise. Okay, so notice that for my transistor to conduct, for this to conduct, the value of V sub I has to be negative. Kasi kung positive yung V sub I, ibig sabihin yung VGS ko will be negative. So para mag-conduct ng transistor na to, for this to conduct, since this has to be positive with respect to this terminal, this must be a negative voltage. Kailangan negative yung voltage na to. So if you don't have a negative voltage, expect this to be cut off. So when I do my plot, I plot for negative values of Vn. I'm going to be plotting for negative values of Vn. Okay. When Vn is 0, you're cut off. When Vn is minus 1, that is when VGS is positive 1. Vn is minus 1, VGS will be positive 1, and that is your threshold voltage. So that is the transition from cutoff to saturation. So this is the transition from cutoff to saturation. And now as I increase the absolute value of Vn, increase the absolute value, actually make it smaller kasi lumiliit yung value, no? Negative kasi siya. Okay, I'm going to go deeper into saturation. As I go deeper into saturation, I sub D is going to increase. What is I sub D? Still your saturation equation, no? I sub D is 1/2 K VGS minus VTH squared. So this is 1/2 K negative VI, VGS is minus VI, minus VTH squared. Okay. So as I increase the negative value of V sub I, this gets larger, this term becomes larger, I sub D becomes larger, the voltage drop across R sub D becomes larger, and my V sub O will become smaller. That's why you see my V sub O now starts becoming smaller. Okay? So this is when it is in saturation. Then at some point it will be in linear mode. And in linear mode, well, ang mangyayari, ang output natin magiging negative. Kasi ang input natin will be very negative, right? Our input will be very negative. VDS will still be positive, okay, but because this is very negative, when you compute for the voltage here, it will still be negative. In other words, the value of VDS will not be large enough to offset the negative value of V sub I. Hindi ma-offset, no? So your output will be negative. And as you continue to make your input more negative, your output will become more negative. But we don't operate the transistor at this point. No? So it's not operated in this area, in this region. For your common gate amplifier, we will confine the operation here. Your operation is confined here. Okay. And so you bias it somewhere in this area. Now, what is your bias? Is it a positive voltage or is it a negative voltage? It has to be a negative voltage. So when you bias this will be biased at negative voltage relative to your gain. Okay. Well, there are so many assumptions here, no? Itong V sub I na to, this assumes that this already contains the bias. That's why this is V capital I, because this already contains the bias. In other words, we're adding, remember V capital I, that consists of an AC component and your bias. This is V capital I. So this is your bias. Then this is your V small I. But later on, when you study actual bias circuits, you're not going to have this. And in this case, no, we said that this has to be negative. No? This has to be negative. When you study actual bias circuits later on, you're going to find out that you don't really have to have a separate power supply. No? We're going to have techniques where you don't need a separate power supply. Okay, so this is your transfer characteristic curve. So we said you can determine a lot from the transfer characteristic curve. First of all, our gain is positive. As you increase, so for example, if I am now operating at this point, and I apply an input signal, okay, my output signal will look like this. Okay? As I increase my input, my output will also increase. My output will also increase. So my gain is positive. In fact, the slope of your VTC will dictate whether you have a positive gain or your negative gain. Kanina yung slope natin pabaliktad, negative gain. Ngayon yung slope natin pataas, it's a positive gain. Okay. You can compute for gain again here. Okay. If I plot the gain, this is what it's going to look like. So you can see the values of the gain that we get. Okay. Okay, this is the last example I have. The common drain amplifier. So your input is at the gate and your output is at the source. Your drain is your common, and with respect to AC, this is actually connected to ground. So these are now the equations that govern this particular amplifier. Your V sub O is just I sub D. Remember that I sub S is equal to I sub D. I sub S is equal to I sub D. And the reason for that is I sub G is equal to 0. Bakit nga ba 0 yung I sub G? Anybody remember? Why is your gate current equal to 0? Yeah, that's right. No? Because, well, when we're doing DC analysis or low frequency analysis, remember what we're doing here is something called brute force voltage transfer characteristic. So we consider each point like your DC point. When you're doing DC analysis, your gate is a capacitor. at steady state, your capacitance is an open circuit. And so your Is of G is equal to 0. So this is technically this is Is of S, but because Is of S is equal to Is of D, then this is also Is of D. And then now VGS, this is now VGS. Okay, is V sub I minus V sub E. No? This is V sub E or V sub O. So V sub I minus V sub E is ID times RE. And VDS is just VDD minus V sub O. So if I write out my equation, for example, in saturation, I sub D is 1/2 K, okay, VGS minus VTH squared. I have to write this. Okay. This is now going to be V sub I minus ID RE squared. That's ID. So medyo mahirap ng konti itong equation na to kasi yung ID nandito, yung ID nandun din. No? So actually, if you expand this is a quadratic equation, in which case there are two roots. Okay? There are two roots. For a given value of V sub I, you can compute for ID, but you will have two roots. Okay? Now, if you are computing, for example, for it's a linear mode, no? Linear mode. Okay, so what is your equation? Your equation is ID is equal to K VGS minus VTH minus 0.5 VDS multiplied by VDS. And if I now plug in these expressions, okay, what is this? This is K. My VGS is V sub I minus ID RD. No. Sorry. Minus VTH. And then my VDS is VDD minus IDRD. So this is minus 0.5 VDD minus IDRD. And then here I have again VDD minus IDRD. So you can see the equation can get a little bit unwieldy, you know. Because you have ID here, tapos meron akong ID dito, tapos meron akong ID dito, tapos meron akong ID dito. That's just plugging this into this expression. So that's a kind of equation that you're going to have to solve. Okay, and this is also going to be a quadratic equation. So anyway, again, using those equations, you come up with this voltage transfer characteristic curve. I won't anymore. I was prepared to actually do some computations here. Let's avoid that. I think you can do that as an exercise. If you take a look at the game, okay, notice that in saturation, so saturation is in this area, okay, your gain is very, very small. In fact, your gain is just a little bit under 1, a little bit less than 1. And in this particular case, it ranges from, let's say, 0.7 to about 0.80, maybe 0.85 or something like that. 0.75 to about 0.85, something like that. Okay. This is the equivalent in your BJT of your common collector or your what you call the emitter follower. So this is also called your source follower. And you use the transistor in this particular case, you use the transistor as a buffer, where your gain is slightly less than 1. Okay. So that's what I have for today. I think it's time. So next meeting, what I plan to do is just discuss some biasing concepts with you. Are there any questions? Any questions? Did everything pass by like a storm? Do you want us to take it a little bit slower next time, or is this okay? Please give me feedback. Anyone want to say anything? Ano, siguro raise your hands na lang, no? Kung nahihiya kayo. You want me to take it a little bit slower? Yes or no? Yeah. So you're okay? Ano yan? Sige. So I'll see you again on Thursday. And then you're going to have a reading break next week. So I think this will be welcome for all of us. See you on Thursday. Yung alin? Yes, sir. If we're not going to have any face-to-face session, then I'm going to make an announcement using either Google or through email. Otherwise, on default natin is face-to-face. Any other question? Okay, so again, see you on Thursday. Thank you.